Hi everyone, my name is Akanksha. I'm a PhD student in Deakin University, and my research is basically to tackle the fundamental challenges which blockchain technology is currently facing. Today I'm going to present my conference paper, which is named as P-sharding. The agenda of my today's talk is we'll start with the introduction to blockchain, then I'll explain the related work, then we will proceed with proposed framework. After that, I will explain the implementation and performance analysis of our proposed framework, and finally the presentation will be concluded. So let's talk about a little bit about blockchain first. Blockchain is basically a peer-to-peer decentralized network having distributed ledger of transactions. You can see in this slide on the left hand side shows the traditional system, which relies on a central server or a third party to get their data verified and stored centrally in a ledger. So if there is any damage happen to this centralized system, whole data will be lost or corrupted and each participant will be in trouble. But on the other hand side, we see the blockchain system. It excludes the reliability on a third party or a centralized server, and transactions get recorded, verified, computed in a decentralized manner. All these peers, they have their copy of ledger through replication, and if any node suffer any kind of damage, others will not get affected, and lost party can get back up from other peers without any trouble. So due to all these features, blockchain has found multiple applications in various areas ranging from finance, supply chain, healthcare, and there are many more. So my research basically focuses on blockchain for healthcare system. So during our study, we identify that healthcare data are not of equal importance. They have different service requirements on the blockchain-based models. For example, emergency medical records need to get processed as per their priority, which currently blockchain is not fully capable to do so unless for a high transaction fee. Also, in the existing blockchain systems, all transactions are considered evenly and processed as first come, first out. Doesn't matter what type of consensus they are using. So we believe this not only restricts the optimal use of blockchain capacity, but also selfish miners can flood the transactions or the network with less important transaction, preventing these emergency transactions from getting processed in a timely manner. And without prioritizing these emergency transactions, fatal loss can occur to patients in hospital as it hinders the real-time access of patients' EMR in emergency medical services. And finally, to optimize the operating expense and capital expenditure, emergency medical services, they have to consider the prioritized transactions prior than the regular ones. So the best of our knowledge, none of these existing blockchain-based models have the provision of prioritizing the emergency transaction, which eventually restrict them to get scaled as well. The existing blockchain platforms such as Bitcoin, Ethereum, they only process limited rate of transactions per second, and that also in first come first out manner, which leads to increased overall latency. It takes longer time for emergency transaction to get fetched from the memory pool because there is no provision for prioritized scheduling, and it cannot be immediately applied to the healthcare system in its present state. Blockchain-based healthcare system can be optimized in terms of scalability in the following ways to handle a growing number of EMR transactions. First can be reducing the communication and computation overhead, and second can be adding resources to a single node, which is known as vertical scaling. Third solution can be adding more nodes to the blockchain, that is horizontal scaling, and it includes the concept of sharding. Now I will move towards the preliminaries or the related research which exists in this area, even though it's very few. So first of all, before we go deep into our approach, I'll give a brief summary of these blockchain-based models, specifically blockchain-based access control models, which start from the users with a decentralized application, famously known as DApp. So these tabs are used by front-end users to render the blockchain-based access control application. An interface between users and DApp is mainly via JavaScript or HTML application in order to establish the communication with the blockchain network. A user can send his access request through these tabs. Then we have the blockchain network, which is very well known decentralized and distributed ledger technology. So blockchain eliminates the need of trust on a third party, and after user sends the access request, it is broadcasted through the blockchain network to each and every pair. Then this network of nodes verify the legitimacy of access request based on the consensus mechanism. Then we have the access control policies. Each peer in the system will have a list of policies which mainly contains access agreements between the owner and the data requester. Mostly in blockchain nowadays, for access control policies, smart contracts have been used. And then we have data storage. So data storage has been a fundamental issue with the blockchain. And considering the limited size of blockchain, some of the existing frameworks come up with the idea of storing data in the cloud while the corresponding hash is stored in the blockchain. So as I've said previously, that to the best of our knowledge, none of these existing models have provision of prioritizing the emergency transactions, and which eventually restrict them to get scaled. So it is of utmost importance to tackle these challenges before commercially integrating blockchain-based access control to healthcare system. Then we move to the preliminaries, that scalability and performance issue which arise due to these. Why these issues arise? So first of all, that every node has to process all the transactions, even though it provides great security, but it limits the scalability to a point that blockchain transaction network can only process few transactions per second. Also, transaction processing rate mainly gets affected by block mining rate, transaction processing, waiting time of the transaction in the queue to get processed. So as I've mentioned, that none of these models have provision to process the prioritized transactions or access requests faster, and they also do not consider the allocation of adequate resources, which is resource fairness. So it's very important to tackle these challenges, and they cannot be ignored in terms of increasing scalability or optimizing the blockchain network resources. So few solutions exist in the literature. One of them is off-chain. In this approach, basically stores transaction-related data in the local nodes, which are often referred to as off-chain data. Another such solution in the off-chain category is creating a network of micro-payment channels to instantly confirm a payment transaction. So such off-chain solution, they cannot guarantee the legitimacy of off-chain transactions, because this validation is happening outside the decentralized system, which is like the validity is compromised due to centralization. Another solution is DAG, Directed Acyclic Graph Network, where each transaction is linked to multiple transactions rather than the blocks. So theoretically, the higher the volume of transaction, the faster a DAG network can validate them. Finally, another existing solutions to tackle the scalability, and which is also extensively explored in the distributed database systems for many years, to alleviate scalability and performance, is sharding. So database sharding refers to the horizontal partitioning that splits large databases into smaller chunks called shards across multiple servers. And now I'm going to introduce our proposed framework, which is P-sharding. The full form is prioritized sharding. So we basically take advantage of sharding concept, and with our analysis we observe that prioritization of transaction directly impacts the scalability of the system. So therefore our system of P-sharding introduces the priority in the sharding mechanism, and in this system, as you can see, that incoming transactions are getting into the memory pool, and then those transactions are distributed to different shards and processed in parallel. So I will explain this whole proposed model in detail in the next slide. So let's understand the idea behind our sharding framework. So first of all, transactions are grouped in the memory pool as they arrive in the system. In every mining iteration, the blockchain is divided into shards. Number of shards, which is the length of the array, is divided according to two factors. First is load, then the number of validators in the network. The transactions are randomly divided among all the shards and get collected in their respective subblock. Each of the shard has their own ledger, and then validator nodes are randomly assigned to each shard. So the transactions with priority are then chosen from these sub-block based on their priority tag. So basically the tag with 0 indicates a non-priority transaction, while 1 indicates a high priority transaction. And the transactions are then sequenced as per their priority and held in the respective priority and non-priority mining queue based on first in, first out approach. After sequencing these randomly selected validators in the network, they will verify the prioritized transactions by allocating their resources prior to the non-priority transactions. Finally, the verified block is generated and added in the sharded blockchain. So this was the basic picture of our proposed scheme. Now let's get a bit deeper into the structure of a shard. So as you can see in this figure, on the upper side we have transaction header and the bottom part shows the transaction payload. In the transaction header we have shard ID, which specifies the ID of the shard it belongs to. Then we have a pre-state root of the shard before the transaction is registered. Priority tag, as I've mentioned, it describes the state of the shard, and our aim of adding this tag is to reduce the response time and maintain service quality for prioritized transaction. While the post root shows the state of the root of the shard after the registration of the transactions. And receive root is generated after all the transactions in the shard are registered, and it also helps in facilitating the cross-shard communication. So, based on the queuing theory principle, the incoming shards follow Poisson distribution. Upon arrival, each shard is either in the priority queue with mean arrival rate of lambda p, or in non-priority queue with mean arrival rate of lambda np. So the total rate is defined in equation 1. It's important to notice here that the waiting time of the non-priority shard in the queue is longer than the priority shard units, which typically depends on the number of transactions waiting to get processed in priority queue ahead of non-priority queue. And then at the end we have a mean queue length of the prioritized and non-prioritized shard. So it's important to notice that our proposed model of P-sharding has some assumptions. First of all, priority queue and non-priority queue, they are considered of infinite buffer capacity to avoid the transaction being discarded in order to maintain the quality of service. Also, in our simulations, we keep all the validators of same capacity for fair play. Although the above assumptions might not be realistic, and we will work on this, in our future research, because queuing is a completely another research domain. Now let's move on to the implementation and performance analysis of our proposed scheme. For the simulation setup, we have simulated our model in a controlled permission blockchain environment on Python. And basically our aim was to measure and compare the overhead of the existing sharding approach and our proposed prioritized sharding model. So as you can see in the figure, our model consists of, we have called them stations. First is source station that consists of transactions. Then we have a queuing station, which is memory pool. And this then we have fork station, which is called P-sharding. Then we have two priority mining queue and non-priority mining queue. Then we have a join station and a discharge blocks. So in this simulation setup, the arrival rate of transaction source station is generated randomly. Then the memory pool is modeled using MM1, where arrival of transaction is Poisson distributed. Service time is exponentially distributed and number of server is kept 1. While on the other hand, mining pool is modeled as MMC, because in reality, several servers compete in parallel to solve a single block of puzzle. The fork station called P-sharding, the main task of this station is to split the transaction based on their priority tag. And it is used to achieve fast processing and reduce service time of transaction in the mining pool. This task is synchronized and forwarded for processing in the mining queues respectively. After all these tasks are processed and completed, they are joined again to dispatch the final block to the blockchain network. So in this table, you can see the input parameters which we have set for carrying out the simulation of Bitcoin and Ethereum using our proposed P-sharding model. And now let's come to the results of I will present the simulated results of our model, which we have basically compared with the basic sharding model, and we have utilized updated Ethereum actual data parameters to carry out our simulation. So the first parameter we have calculated is mining queue count, and then we have response time. So I can here the upper figures are the simulated results with our proposed scheme, and the bottom figures are with the actual basic sharding models. So then we have throughput and utilization. So mining queue count are the accumulated sharding transactions which are waiting in queue to get mined, and due to probabilistic approach, the priority mining queue has more sharded transaction than the non-priority mining queue. And also it gets improved significantly as compared to the basic sharding you can see in the bottom, because in basic sharding model all transactions are considered equally, irrespective of their priority. Response time is the average mining time of a sharded transaction, or we can say mining time of both priority and non-priority mining queue. It is almost same with negligible variations due to dynamic arrival and mining rates. Then we have throughput, the rate at which transactions depart from a mining queue. That is the number of transactions completed in a unit time. So here we can see that a priority mining queue has higher throughput. That means mining of a prioritized transaction is faster as compared to the non-priority mining queue. Utilization can be defined as a percentage of a time a station is used. That means busy. It ranges from 0% when the station is idle, doing nothing, to the maximum 1 or 100% when it's completely busy mining transactions for the entire simulation. So you can see in the priority mining queue, the utilization rate is 1.8 into 10 raised to power 3, which is 10 raised to power minus 3, which is less than 1, means priority mining queue is not fully occupied. So our system achieves high utilization rate, while in the basic model system is congested due to a high utilization rate. So this table further validates our model and shows the comparison between actual and simulated results of basic sharding and our proposed model. The values indicate significant improvement in these stated parameters with our proposed scheme compared to the basic sharding model. Now I'll finally conclude this presentation. So in this research, we have proposed the first ever approach of prioritized sharding to streamline the processing of prioritized transactions in a blockchain-based model. It has improved the processing rate of prioritization drastically, which we can see in the simulation results. Also, the mining congestion got reduced with our proposed model as the waiting time for transaction confirmation reduces. The quality of service also improved in context of prioritized transaction as compared to the existing blockchain, sharded blockchain. Finally, in our proposed scheme, the performance of a high-level blockchain-based model has also been evaluated, which gives a wider picture in how to develop a scalable and efficient access control model for healthcare. Even though we have shown the advantages of our model, but in certain ways, our model still requires a more in-depth evaluation of how validators come to a decentralized consensus to select the emergency transaction and avoid selfish mining. And also in real scenario, there exist transactions with varying priorities. So therefore, we should include them with and implement the whole system on a larger scale. Further, to enhance interoperability, it is important to analyze the work on the cross-shard communication to efficiently share prioritized electronic medical records across different blockchain models. So yeah, these are our future work, and I will conclude my presentation. Thank you so much for listening.